Hi there. So today what I'm going to do is I'm going to talk a bit about the maximum shear stress that you can have from a given loading, right? Last video, hopefully you've watched it. If you haven't, you think you need to, has to do with the principal stresses. Those were the biggest and smallest normal stresses, right? This is our starting point again. We have some stress state with a x normal stress, a y normal stress, and a shear stress. The principal stresses, which were the largest and smallest axial or normal stresses, were equal to this, sigma P1 and sigma P2. There's two of them in here. It's the average normal stress, right? If you want to mark that off for yourself, it's the average normal stress plus or minus this square root of sigma x minus sigma y over 2 squared plus tau xy squared. Let me mark that off for myself here. This first term was the average normal stress, right? Sigma sub AVG. This second term we'd called R, okay? There's a reason for R coming later. Right now, just call it R, and if you're thinking, we normally use R for radius, yeah, that's where we're going, okay? The planes that we had, the directions, were at theta P equals 1/2 the arctangent of shear stress divided by this sigma x minus sigma y over 2. Yes, it's the same term that's sitting inside the square root, right? That denominator is the same thing as the first term under the square root. That got us the principal stress. Something we're also going to want to know is what the biggest shear stress happens to be in that plane, okay, in that xy plane. And again, what we're going to do here is for the xy plane. We'll see later that there's something different in 3 dimensions than just in the plane, right? And they may come out to be the same. It might be that the largest shear stress we can have is the one that's in the plane, or it might not. So if it sounds like I'm being extra careful about saying this is in the plane, that's why, because, well, that's all I can say definitively, okay? So this down here, finally got through the background here. This was our equation a couple times ago here, a couple videos ago, for the shear stress in the plane, in some direction nt if we've done a rotation, right, based on sigma x, sigma y, our angle of rotation, and our shear stress. It's minus sigma x minus sigma y over 2, and there's that term again, times sine 2 theta plus tau xy cosine 2 theta. Deep breath. Now what, right? Last time, what we did to find the principal stresses is we used the first derivative test, right? Calculus says we have the maximum or the minimum where the derivative is equal to 0. It's no different. Let's do it again, right? So let's take that first derivative. Let's apply that first derivative test. Apply that little first derivative test here. And we're going to set that first derivative equal to 0. So it's going to be d tau nt d theta is equal to, well, I need the derivative of that first term. And blessedly enough, since it's with respect to theta, I don't see a theta in that leading term at all. And now I need the derivative of sine 2 theta. Well, that's just going to be twice cosine 2 theta plus tau xy. And because that doesn't have a theta in it, and now I need the derivative of cosine 2 theta. Well, that's just negative 2 sine 2 theta. I'm going to say that that's equal to 0. And I'm also going to say that's equal when theta is equal to some angle theta sub s. Why theta sub s? Well, we had P for principal, S for shear. Go figure, right? Make it nice and simple. Okay, so what we can do then is, first thing I do is I see those 2's, and yeah, I could knock the 2 out from the denominator of this sigma x minus sigma y. I don't want that. This 2 and this 2 can both go, okay? And what I also have is I technically have a negative on both of these terms, right? So this is actually equal to, I can say this derivative is actually equal to sigma x minus sigma y over 2. Actually, let me get rid of this equal sign here. This actually doesn't make any sense to me. It makes more sense if I just write it as sigma x minus sigma y over 2 times cosine 2 theta s plus tau xy sine 2 theta s is equal to 0. Where what I've done again is I've knocked out the 2's and I've knocked out the negative sign that leads off the first term and the negative sign inside the parentheses on the second term. Okay, so that's how I have this equation. Last time, when we did the principal stresses, we said, hey, sine divided by cosine equals tangent. Let's solve for tangent of 2 theta s, or 2 theta p that time because it was principal. We're going to do the same thing just for theta s instead of theta p. It hopefully looks like it's something similar, right? So I can do some manipulation. The tangent is the sine divided by the cosine, so tangent 2 theta s is going to equal, and this is where things are going to get a little bit different. It'll be minus the quantity sigma x minus sigma y over 2 divided by tau xy. Right? And I could also call this, by the way, nothing says I couldn't put the negative in the denominator, right? If you want to have negative tau xy in the denominator, fine, whatever. 6 and a half dozens, as they say, 6 and 1/2 dozen of the other. Remember that triangle we drew last time, okay? It's going to get us somewhere. Because last time, what we did with the principal stresses, I keep saying last time, and when I refer to last time, by the way, I'm thinking of the principal stresses, right? Because this is exactly the successor to the principal stress video, right? So I do the triangle from the principal stress, and it's going to be similar. And we'll see exactly how similar it is in just a second. Okay, so I can say, and I'm going to draw it just slightly differently. Okay, because really, if I want to deal with, say, the negative, I'll put the negative on the tau xy, right? And I'll call this negative tau xy. I'll call this distance sigma x minus sigma y over 2, because then I can call this angle in the corner 2 theta s, and I have a right triangle. Okay, I've got opposite sigma x minus sigma y over 2 divided by the adjacent negative tau xy. Now you're seeing why I drew it in the left corner of the triangle. It looks negative if, say, for example, I put my x-axis in here. It looks like it's negative. Great. Isn't that fun? Well, a couple other things about this triangle is going to come up in a minute. But what we're going to be able to say now is that if I call this distance here r, wait a minute, why am I using the same variable that I did last time? I mean, geez, I better be getting the same thing. Well, Pythagorean theorem says r is equal to the square root of the quantity sigma x minus sigma y over 2 squared plus squared. Make that 2 look more like a 2. Squared plus tau xy squared. That is the same thing as last time. It's the same r. Beautiful, right? This is kind of convenient. So I can still do the same thing with the sine of theta and the cosine of theta. In this case, though, the sine of 2 theta s is going to be the opposite side, sigma x minus sigma y over 2, divided by the adjacent, by the hypotenuse, I should say, r. And cosine is going to be the adjacent negative tau xy divided by the radius, r, right? So cosine of 2 theta s in this case, is going to equal minus tau xy over r. Sine of 2 theta s is going to equal sigma x minus sigma y over 2 divided by r. Okay, great. Now I can put this back into my tau nt equation. Scrolling up for a sec. This equation at the top of the page, I've got to put that value of theta into that equation, and that will get me my maximum shear stress in the plane. Let's go. All right, so tau max, with the understanding that this is just the maximum in the plane. I think I've said that about 100 times, and it's worth, I'm probably going to say it 100 more, right? It's equal to the quantity sigma x minus sigma y over 2. Ooh, that was interesting. Word decided to do something strange to me. Over 2. And there's a negative out front of this. Times the sine of 2 theta s. Well, that's just sigma x minus sigma y over 2 divided by r. And this is plus tau xy times the cosine minus tau xy over r. That's what the cosine was. So then what I can say is that tau max equals minus, and this is looking more like tau min, you might be saying, because it's got a minus on it, and you're right, but more on that in a second, plus tau xy squared. I'll make sure we're explicit that that's all inside parentheses. There's a negative on both those terms. Divided by r is equal to minus r squared over r is equal to just minus r. So what we say is that one plane is going to have a clockwise couple, one plane is going to have a counterclockwise couple, so that one side has a negative, one has a positive. So what we wind up being able to say is that really tau max is equal to plus or minus, and this is really tau max and tau min. We just leave it as tau max, right? Is equal to the square root of the quantity sigma x minus sigma y over 2 squared plus tau xy squared. And this is the value of our maximum shear stress. Okay, gonna lean back, push back in. Whew. But now what, right? Be great if we knew something else about theta s. And we can say something. And I've got two ways to say it. The first one's going to be kind of graphical, and the second one's going to be more, shall we say, mathematical, analytical. See, we have this 2 theta s angle in the triangle, right? And I've scrolled up for that reason. Well, last time when we did the principal stresses, we put 2 theta p in that part of the triangle, right? Because we had sigma x minus sigma y over 2 on the adjacent side and tau xy on the opposite. That means that angle across the vertex is also 2 theta p. That's one way to look at it. So therefore, they have to be separated. 2 theta s, 2 theta p have to be different by 90 degrees, plus or minus. Let's go one more step than that, okay? If you look carefully at that tangent of theta s, tangent of 2 theta s, you'll see that's actually equal to negative 1 over the tangent of 2 theta p. When we had theta p last time, its tangent was equal to tau xy divided by sigma x minus sigma y over 2. Well, I've got negative 1 over that now. And the way that the trigonometry works out, this means guaranteed 2 theta s is equal to 2 theta p plus minus 90 degrees. Therefore, theta s is equal to theta p plus minus 45 degrees. The principal stresses and the maximum shear stress, their orientations, if the principal stresses are here, the maximum shear stresses are 45 degrees away. Always. Every time. Guaranteed. You've got to have that. Okay? So that's one thing. Now, here's something else fun. We haven't answered one more question. When we did the principal stresses, we knew full well that the shear stress had to be 0 because the shear stress was the first derivative of the normal stress, and therefore we had maximum and minimum when the shear stress was 0. What's my axial stress now? It's not necessarily going to be 0. Okay? There are cases where it is, but those are special, right? In this case, we're going to have to look at what those stresses are. So, sigma n f theta equals theta s, right? What I'm going to get, sigma n equal to sigma x equals sigma y over 2 plus the quantity sigma x minus sigma y over 2 cosine of 2 theta s, the cosine, was negative tau xy divided by r, right? So therefore this is going to be times negative tau xy over r plus tau xy times the quantity minus sigma x minus sigma y. Sorry, I don't have a negative sign on there. I apologize. So that's times sigma x minus sigma y over 2 all over r, okay? That's the sign with sigma x minus sigma y over 2 all over r. I'll scroll up just again so we can believe it again. This was my sine function over here on the bottom right of the page. Therefore, I have this. Notice the second and third terms are the negative of each other. This and this cancel. Sigma n is sigma x plus sigma y over 2. We can do the same thing for sigma t. I feel like being more clever today, though. Right? I can get sigma t real quickly. Since sigma n plus sigma t, if you remember from the stress transformations, the sum of the normal stresses doesn't change as I change my orientation. Sigma n plus sigma t has to equal sigma x plus sigma y. Therefore, sigma t is equal to sigma n, and I called this sigma x plus sigma y over 2 the average axial stress above. Well, they both have to be equal to the average axial stress. And that's what the shear stress, sorry, the average axial stress is. That's what the axial stresses are, I should say, at the maximum shear stress. When we have the maximum shear stress, the axial stresses are equal, and they're equal to the average of the axial stresses, period. That's what has to happen. So, all we have left is really to draw some stress blocks here. Now we're going to draw 3. Last time, you might remember at the end, I drew 2 for the principal stress and for the generals and for the initial stress state. Now I'm going to throw in a third one for the maximum shear stress block. Okay, so the way this all looks. This is one way to represent it. I think it's a pretty handy way to represent it, actually. There's sigma y, sigma x, and again, all this is drawn positive, but there is no reason why we can't have negative sigma x. It would just be compressive. We can have negative tau xy, would just be flipped. No big deal, right? And again, we're going to have our x, y axes. Last time what we did is we drew a line going up. We're also going to draw a line going down now. Okay, and the way these turn out, this direction on top, this angle, is going to be by an angle equal to theta p. I got choose on the brain. It's easy to do when you're doing this, right? That's theta p. The angle on the bottom is theta s. Therefore, the total angle in here, theta s equals theta p plus minus 45 degrees. That total then has to be 45 degrees. My stress block for the principal stresses is going to be sigma p1 and sigma p2. This is under the assumption now that sigma x is bigger than sigma y, because sigma x rotated to be sigma p1. And then this other block, if I can put some axes on the first one, of course, call them P1, P2. I'll draw my axes outside the block because I made that block relatively small. Call them S2, S1. I'm going to have my shear stress like that. tau max I'm going to have the axial stresses equal to sigma average in both the S1 and S2 directions, right? This is what the complete situation looks like. If I have an initial stress state now, I rotate one way. It could be up or down depending on how things work out, how the angles work out. I get to the principal stresses, which have no shear stress. You see there's no shear stress on that stress block on the top. And again, the way I drew it, since sigma x rotated to be sigma p1, I had sigma x bigger than sigma y. If that was reversed, then sigma p1 would be going on this in the sort of vertical direction, and sigma p2 would be going the sort of horizontal. But that's just the other case, no big deal. And then I rotate 45 degrees, either this more the same direction, or it's easier to draw if I rotate the other direction. If I rotate 45 degrees from theta p, I get theta s pointing the other direction, pointing downward in this case, where tau max exists. I have the maximum shear stress, which is equal to the radius, and my axial stresses there are both equal to the average normal stress, sigma x plus sigma y over 2. Everything here, we have equations, sigma p1, sigma p2 up above, tau max up above. It all comes down to what's on that initial stress block. We can find all of this information using only what we had in terms of the initial loading. What this does for us then is it lets us pick a convenient coordinate system. Set it up as nice as you want. Make the analysis as nice as you want. And then what you do is you work from there, and you can get the principal stresses every time. You can get the maximum shear stress every time. One more thing, right? Notice how the stresses are equal. The axial stresses are equal when we have maximum shear stress. So if I have a state of pure shear, I just take and twist my little stylus here, right? I have no axial stress in this coordinate system where my x-axis is left to right on my screen here, right? The x-axis is lined up with the stylus. I have no axial stress there in the x or y direction if I'm just twisting it. Therefore, sigma x and sigma y, so to speak, are equal. I know then that I'm looking at the maximum shear stress. If axial stresses are equal, you've already got the maximum shear stress. Just like if your shear stress is 0, you've already got the principal stresses. That's the way you can tell when you have the maximum shear stress. Okay, thanks for watching, and see you next time.